I am Lakshmi Prasanna, Assistant Professor, Department of ECE, Institute of Aeronautical Engineering. Welcome to the lecture session of image processing. In this session, we will learn about some basic gray level transformations. So, in the topic, we are going to learn in detail about different subtopics like image enhancement. That means what is the purpose of going for image enhancement, and spatial domain. So as we are learning about module 2, which is image enhancement, so we will learn image enhancement in two domains. One is spatial domain and frequency domain. Now we will learn about spatial domain. What is spatial domain? How to represent an image in the spatial domain. What are different techniques in the spatial domain in order to enhance the image. And next is intensity transformation applications. So in this intensity transformation applications, we are going to learn two. That is, one is contrast stretching. So why we need to go for contrast stretching? So what will be the output after contrast stretching? And one is image thresholding. Next, we will see about intensity transformation functions. Here, there are different intensity transformation functions available. One is point transformation, linear transformation, log transformation, and last one is power law transformation. So, all these are the 4 functions of intensity transformation. Along with this, in this linear transformation itself, there are different subtopics available. We will also learn about this log transformation, not only log, and inverse log also we are going to learn, and power law transformation. So here, first thing is image enhancement. So why we need to go for image enhancement? So generally, we have seen in the previous sessions fundamental steps of image processing. In that fundamental steps of image processing, the first step is image acquisition. After image acquisition, next step is image enhancement. So we are going to learn here image enhancement now. So as soon as the image is captured by the capturing devices, if we see that particular image, that image will not be clear. So it will be a poor quality image. So it is very difficult to extract the complete information from the images. So generally, in which cases the captured images will have a low quality means the image may consist of some noise, or the lens what we have used during capturing may not be placed properly, or due to some noise. So due to all these reasons, the captured image may be poor. So here, our intention is in the image enhancement, we have to improve the quality of that particular image. So improving the quality of that poor image is called image enhancement. So in some of the captured images, it is very difficult to extract the complete information from images because it may consist of some noise, or the captured images may be blurred images. So it may be a poor quality image. To extract the complete information from the image, we have to process that particular image. So processing that image means we have to apply some transform on that image. Operator should be applied on that image. So this entire process is called image enhancement. So improving the quality of the image by applying some transformation is called image enhancement. So here the image processing operations, in order to enhance the image, we can apply spatial domain or frequency domain. So now in this module, we will look image enhancement in both the domains. That means image enhancement in spatial domain and image enhancement in frequency domain also. So first let us learn how image enhancement will be done in spatial domain. So we need to know what is meant by spatial domain. What is the basic difference between spatial domain and frequency domain? So here coming to spatial domain operates directly on the pixel. So any image element will be represented in the form of a pixel. For example, if you consider this is a image. So if we have here, consider as a pixel which is present at the origin. So its coordinates will be its coordinates will be 0, 0. Okay. So in the spatial domain, it operates directly on the pixels. So this is the pixel where the operation will take place directly on the pixel. And here, this is a 3 by 3 neighborhood. So if we consider here the middle part as one pixel, which is represented with coordinates x, y. It is represented in the form of 3 by 3 matrix, and except this, the pixel which is at the center, if you see here, the remaining pixels, these are all the remaining pixels which are called neighbors of this pixel. So this is the representation of 3 by 3 neighborhood at the point x, y in the image. So in the spatial domain operates directly on the pixels. So for example, in the frequency domain, how it operates means, first the image will be represented in the spatial domain, and the image which is represented in the spatial domain should be converted into transform domain. So here the basic transform what can be applied is Fourier transform. So after this transform domain, that will be converted again into inverse transform domain. That is, inverse Fourier transform will be applied. It will be in the frequency domain, and again this particular image will be converted into spatial domain. So this is the operation that will happen in the frequency domain. So in frequency domain, it will not operate directly on the pixel. First, it will be converted into, it will be represented in the form of spatial domain. Next, it will be converted into transform domain. After that, it will be converted into inverse transform domain. Next, it will be represented in the form of spatial domain. So this is how the operation will be performed on the image in case of frequency domain. Whereas in case of spatial domain, it operates directly on the pixel. So this is the major difference between spatial domain and frequency domain. So we will learn about this frequency domain in detail in the upcoming sessions. Now we will concentrate on this spatial domain. Now, so here spatial domain will be indicated with the expression g of x, y is equal to t of f of x, y. So what is this f of x, y? F of x, y is the input image, and g of x, y is the output image. So output image can also be called as processed image. And here on the input image f of x, y, here we are going to apply transform. Then the output what we are going to get will be the processed image, which is called as output image. It is represented as g of x, y. So this is the basic representation in case of spatial domain. So here we have represented f of x comma y is called the input image and g of x comma y is the output image and t is the transform or operator what we are going to apply on the input image f of x comma y. Now, so the same expression can be simplified as S is equal to T of R. So here S is equal to G of x comma y, whereas R is equal to f of x comma y. So we will call this S as the output image or processed image and this R as the input image, pixel value of the input image, and this T is the transform or the operator applied on the input image. So after applying the transform or after applying the operator on the input image, then the image what we are going to get as the output is the processed image, which is the enhanced image. Now, so in the spatial domain, if you come across this intensity transformation, we have different applications of this intensity transformation and here are the applications. One is contrast stretching, another one is image thresholding. So here what is meant by contrast stretching and what is meant by image thresholding we will learn. So first thing is, what is the necessity of going for contrast stretching? So what is the purpose of contrast stretching? Here, in order to improve the quality of the image, we need to go for contrast stretching. So in this case, if we want to discuss, it can be clearly discussed with the help of this function. So here in this graph, we can observe. So here there is a contrast stretching. So here we can see M. So this M represents it is a threshold value. And here, as we have seen in the previous slide, the spatial domain, general formula how we have represented, S is equal to T of R. So where R represents the input image and S represents the output image. So in this graph, here, this is R on the x-axis, that is pixel values of the input image are represented on the x-axis, and pixel values of the output image S is represented on the y-axis. So here we can see the transfer function. Okay. So considering here M is called threshold value. So this value of M may be greater than R. The value of M may be less than R. So if the value of M is greater than R and if the value of M is less than R, how the intensity in the image will be changed? So if you see here, in case of R less than M, so this is the value of R. So all these are the values of R. Okay. So if the value of M, considering the value of M, if the value of R is less than M means R value will be lying somewhere here in this region and here is the M. So if you consider here up to here, it will be represented like this, and this region is called dark region. On the y-axis, if you see, this region is called the dark region. So if the value of R is less than M, then the narrow range of intensity level of F will be towards dark region. That means that particular pixels will be represented as black color. In another case, these are all the values of R. In another case, the value of R may be greater than M. So this is the region somewhere the value of R will be present. If the value of R is greater than M, so if you extend this and this is the threshold, so this is the area what we will get, and this area is represented as light. Okay, so here light means bright color. So whatever the pixel values that are available here, they will be represented with the help of white color. So here clearly given, if the value of R is less than M, it is considered as a dark region. That particular pixels will be given as black. If the value of R is greater than M, that particular region will be represented as bright region. Why? Because that pixels will be colored with white. Now, so this is how the contrast stretching will takes place. So here the value of what is here R represents the pixel values of the input image, and here M represents the threshold value of pixel. Now, so in the intensity transformation, coming to the second application is image thresholding. So here also one threshold value will be considered. So in this case also we are considering the threshold value as M. So this image thresholding concept is generally applied for the binary images. That means if on any image, if this image thresholding concept is applied, then the resultant image what we are getting will be the binary image. That means the binary image means it consists of only two pixel values. One is 0, another one will be 1. So whereas 0 represents black color and 1 represents white color. So as this particular image consists of only these two pixels, that image is called binary image. So the entire image will look like only it will be either black or white, no other color in between. So in this case also, here pixel values of the input image is represented as R. So as we have seen the function in the intensity, it is represented as S is equal to T of R. So where R represents the pixel values of the input image on the x-axis, and S represents the pixel values of the output image on y-axis. And here M is the threshold value of pixel in the input image. So if you consider here, these are all the values of R. So if the value of R is less than M, if the value of R is less than M, here, if the value of R is less than M, then it will be towards darker region. If the value of M is greater than R, see here. So if the value of R is greater than M, it represents bright region. That is, that particular pixels will be represented with white color. So this is what about contrast stretching and image thresholding, that are applications of intensity transformation. Now, so we have learned about intensity transformation applications. Now coming to intensity transformation functions. So here there are 4 types, 4 functions are available. So first one is point transformation, next is linear transformation, log transformation, and power law transformation. So all these are the 4 intensity transformation functions. So we will discuss about each function in detail. So the first one is about point transformation. So point transformation is the same thing what we have discussed. It directly operates on the value of the pixel in the image, what we have discussed in the previous slide. So this point processing can be represented as S is equal to T of R. So here R represents pixel value of the input image, S represents pixel value of the output image, and T is the transform applied on the input image R. end. Next transfer function is linear transformation. So intensity transformation function, first one is point processing and the second one is linear transformation. So this linear transformation is of two types. One is negative transformation, another one is identity transformation. So we will learn about negative transformation and identity transformation in detail. Coming to the first type, that is negative transformation. So why it is named as negative means? Negative means, so if the input image is of white in color, the output image will be occurring as black. If the input image consists of black in some regions, it will be represented as white in the output image, that is processed image. That's why it is called as negative transformation. So here what is meant by negative transformation means, negative images are useful for enhancing white or grey detail embedded in dark regions of an image. So what happens here means, the dark values will be exchanged with light values. That means black color will be exchanged as white and vice versa. White will be exchanged as black. So this negative transformation will be represented with a formula S is equal to L minus 1 minus R. So here what is this L minus 1? So for example, if you are considering any 8-bit image, so the number of intensity levels will be 2 power 8, which is of 256. So the pixels values will be ranging from 0 to 255. That means 0 to L minus 1. Now, so S is equal to L minus 1 minus R. So here R is the pixel value of the input image and S is the pixel values representing the output image. So negative of an image intensity levels will be ranging from 0 to L minus 1. So L minus 1 is the maximum pixel value, 0 is the minimum pixel value, and R is pixel value from the input image. So here 0 represents the minimum value, which will be represented as black, and L minus 1 is the maximum pixel value, which represents white, and the values that are present in between this range will be represented as shades of black and white colors. Now, so this image, from this image we can clearly understand what is this negative transformation. So this is the input image. That means this is the original image which is captured with the help of mammogram, and after applying this negative transformation technique, this will be the output image what we have obtained after applying this negative transformation. So if you see here, so this is the area where we can see all the black color. If you apply this negative transformation in the output image, this entire area will be represented with white color. So you can see here, this entire area here, it is white in color. And whatever here, the regions that are represented here with some white color, so here it is represented with black. Okay. So after applying negative transformation in the input image, wherever the dark regions are available, it will be converted into white, and wherever the white regions are available, it will be converted into black. So this is what about negative transformation. Now, so this is the graph we have obtained from this negative transformation. So how we have obtained this graph means, we have seen the equation related to this negative transformation, that is S is equal to L minus 1 minus R. So if you consider any value, so this is here R, and here this is S. So for example, as we have discussed, so what will be the value of S? If L minus 1 is 255 minus, if the value of R, for example, initially let us consider at the origin 0. So the value of S will be 255. So for the value of R, S will be 255. So here is R because it is on the x-axis. So you are going to get S value as 256. Similarly, if the value of R changes, for example, S is equal to L minus 1 is 255 if we consider 8-bit image minus. So if you come to the next value of R, for example 1, it will become S is equal to 254. So here S value will be 254. Sorry, S value will be 254 for the value 1. Okay, so like this, if we join all the points by considering different values of R, then the graph will be looking like this. So this is the graphical representation of negative transformation. Coming to the second type of linear transformation, after negative transformation, the second type is identity transformation. So what happens in this identity transformation means each value in the input image is directly mapped to each value of the output image. That means input value and output value both will be same. That means if input and output values both are same, then there will not be any change in the output image. Input image and output image seems to be same. So the result will be whatever the input image and the processed image, that is output image, both will be same. So this is the graphical representation of identity transformation. So here these are the values of R and these are the values of S, output image. So whatever the value is there in the input, the same value will be there at the output. So whatever the value is there at the input, the same value will be there at the output. So if you combine all these points and if you join all these points, the curve will be very linear. And next intensity transformation function is log transformation. So next intensity transformation function is log transformation. So in this log transformation, here we are going to discuss about log transformation and also inverse log transformation. So coming to log transformation, it is represented with the formula S is equal to C into log of R plus 1. So here S represents the input pixel value and R represents the input pixel value and S represents the output pixel value. Here C is constant. So the value of C is constant. So if we observe here, we have added the value 1. So there is a reason why we have added the value 1. So if we want to add the value 1, at the initial case, the value of R may be 0 because here if you consider R will be there on the x-axis. So the values of R will be starting from 0, 1, 2, 3, 4, so on. So if the value of R is other than 0, no problem. Initially, if we start the value of R from 0, so S is equal to C log 0 we will get. If we won't add plus 1, we will get S is equal to C log of 0 where its value is equal to infinity. So in the formula we can see 1 is added to each pixel value because the pixel intensity for the pixel intensity 0, that is for R value if it is 0, you are going to get the value of S as infinite. So we have to reduce that. For that purpose, we are going to add this plus 1. So the formula S is equal to C log of R plus 1. If you go for different values of R and the value of C as constant, we can get this graphical representation. So here on x-axis we will have R, and on y-axis we will have S. So where S is equal to, so the formula we can see here, S is equal to C log of R plus 1. So if you go for different values of R and substitute here and taking the value of C as constant, you can get different values of S, and if you plot the graph, it will be looking like this. So what happens when this log transformation is applied on the input image? So if log transformation is applied on the input image, the dark pixels are expanded compared to the higher pixel values. So here only the values whichever are dark, they will be expanded, whereas the higher pixel values will be compressed. We can see in the figure. And coming to inverse log transformation, it is exactly opposite to log transformation. So this is the graphical representation of inverse log transformation. So if you consider this figure, it will clearly show, so this is the input image. So on this input image, we can apply log transformation or inverse log transformation. So if log transformation is applied, we are going to get the output image like this. So what we have observed in this image compared to the input image, this image is changed, processed. So what happens to the input image here means, when log transformation is applied, the dark pixels are expanded and the higher pixel values are compressed. And coming to inverse log transformation, that means on the applied on the input image, if this inverse log transform is applied, then this is the resultant output image. So if we observe this image, we got exactly opposite to log transformation. That means here dark pixels are compressed, whereas the higher pixels are expanded. Next, so the fourth intensity transformation technique is power law transformation. So this type of transformation is used for enhancing images for different types of display devices. So we can see different types of devices. In all the devices, we can have different types of displays. So the formula to represent this power law transformation is S is equal to C into R power gamma. So here R represents the input pixel value and S represents the output pixel value. And in this case, C is constant, whereas here this is the value of gamma and this value is also constant. But see that the values of C and gamma should be real numbers. Okay. So the display devices, the intensity of the display devices can be varied by changing the value of this gamma. So that's why this is also called as gamma correction. Okay. So different display monitors display images with different intensities. So and clarity, because every monitor has built-in gamma correction in it with certain gamma ranges. So here we can take the value of gamma from 0. The value of gamma may be greater than 0 or the value of gamma may be less than 0. So based on all these cases, we will see if you consider these values of these ranges of gamma value, how the intensity will be changing. Now, so we have seen what are all the different values the gamma can have. In the first case, let us consider the value of gamma is greater than 1. So gamma is greater than 1. So when the value of gamma is greater than 1, it stretches the contrast in brighter areas and compresses the pixel values in the darker areas. In another case, consider the value of gamma is less than 1. So if the value of gamma is less than 1, it enhances the contrast in dark areas and compress the pixel values in bright areas. So these two are exactly opposite. So here we can see the plot which consists of different values of gamma. So here gamma value is equal to 1. If you come below that 1.5, 2.5, 5, 10 and 25. So the gamma value is greater than 1. If you go for these ranges 0.67, 0.40, 0.20, 0.10, 0.04, all these are the gamma ranges that are less than 1. Now, so here this is the image that shows the example for different values of gamma. Whereas in this example, the three values of gamma, what we have considered, are greater than 1. So for example, here the gamma value is equal to 6, here it is 8 and here it is 10. All the gamma values are greater than 1. So in this case, if the values of gamma are greater than 1, it stretches the contrast in bright areas and compress the pixel values in the dark areas. See here, initially the gamma is 6. Next the gamma value has been increased. So the quality of the image has been enhanced. And again the value of the gamma is increased. So here compared to all, this is what the image somewhat looking better. So all these are the 4 intensity transformation functions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.